what we're going to do now is we're going to design some context-free grammar. So we see some previous examples last time for designing these. I thought I would emphasize a couple of interesting design techniques, namely when we have a pattern we're trying to seek out. So we're going to start off with a simpler one first, then we'll do one that requires a little bit more thought. So let's consider let's design a context-free grammar. Context-free grammar for the following language. So I'm going to describe the language to you, and then we're going to try to come up with a way to describe this in terms of a grammar for the following language. And I must stress that this language is one that we've actually seen in the past. So there's nothing going to be overly scary about this language. However, I would like to describe it using a grammar. So suppose I give you a string W. It's going to be consisting of zeros and ones. So it's going to be a binary string such that the length of W. So if I look at the length of the string, I want to know if it's even or not. That's another way I could put this. I want to know, so it belongs to this language if the length of the string is even. Gonna go, bye-bye. Boo! It's gone. You might ask, what should we try doing? So I'm gonna pick up a couple of ideas that we had in the past. And you gotta think about this in terms of generating a string. So generating a string. So the first thing we know is that this is going to be a binary string. So just for example, the empty string, which I'm going to write as epsilon here, this has length 0. So technically this belongs to this language because it's a string that has no symbols, making its length 0. Likewise, this string also has an even length. It has length 2. Does this string belong to the language? 110? Does that belong to the language? Well, look at its length, right? Is it even or odd? So would this belong to this language? As in, is the string's length even or odd? That's all good. That's all good. I got the idea. It's pretty awesome. So this guy is just odd, right? So this, the empty string belongs to the language. This belongs to the language. However, this one does not because it has an odd length. However, one like this with length 4 most certainly belongs to the language. So the thing that you really have to keep in mind when we're trying to design a grammar for this, or at least one way we could go about it, is that it doesn't really matter if there's zeros or ones. What we care about is the length of the string. That's all it requires us to be a string in this language. So if I want to generate any one string of this language, think about it like this. So you know its length is always going to have to be even. And that means that I want to take this idea of having any binary string. So I'm going to restrict this so that its length is even. So here I'm going to present to you an idea. Here's an idea. So imagine I have this, and this is supposed to represent a counter for how long the string is. So here's an idea. Here's an idea. If I'm sure that every single time I consider a production rule, that I don't put just one symbol into the string, I always include 2 symbols at a time. If ever I look inside my counter of how many symbols are in the string, it's always going to be even or odd. So for example, if I apply a production rule, I make sure I always include 2 symbols, regardless of what it is. So if I were to apply a different one, it always has to be that it's some even number. So now I have a length 4, and I can keep doing this. Now, you might ask, how are you going to do that? So that's the big kicker. Now, one way we could go about this is let's create a production rule. So first we know right away that this is going to be our start symbol. We know it's going to produce the empty string. That we know because it belongs to this language, right? Because strings of length 0 most certainly have an even length. But we're also going to use this to help us effectively terminate this process, to terminate the process so that when we're done applying production rules, we could just cleave this process off, and now we end up with our sentence. So here's an idea. Well, how many ways could I write out 2 symbols that I could always include? Well, I can include 0, 0, 1, 0, 0, 1. So I got 4 different patterns, right? 0, 0, 1, 0, 0, 1, and 1, 1, right? Now let's take an idea that we've seen when we were studying palindromes. So whenever I apply this, so notice that that's just a pattern. These are all possible ways I could introduce 2 symbols into the string. I want you to imagine that it's like I'm going to put my fingers into water and it's going to cause water to ripple away every time I apply a production rule. But notice that if I include all these patterns, it doesn't matter. I'm always going to end up with an arbitrary binary string. But I would like to always make sure, just like with my counter, I always put in 2 symbols every single time. So here's an idea of how I would go about this. So I can go 0. So we had 0, 0, right? So I could have 0, S, 0. So notice that if I do this, I can introduce this variable s so that I can reapply the rule. Just like if I were to put 2 more symbols, my counter, I could make sure it's always even. In this case, all it's going to do is create a whole bunch of strings with a bunch of zeros in them, right? Because every single time I can replace this, I can add 2 more zeros and a variable in between. So naturally, once you see this, you could keep doing this, right? So I could just go through each one of my patterns here. And I go 1, S1. And notice here that just as an example, if I wanted to produce a string for you, just to illustrate my concept here. So notice that if I were to start off with S, if I apply, say this production rule right here, I get 1, S1. Then I could apply maybe this one right here. So then I got 1, 0, S1, 1. So that's the new part that I've replaced S with. And I could just simply apply the first production rule, the epsilon there, and I end up with 1, 0, 1, 1. That most certainly belongs to the language, right? Do you see every single time I apply the production rule, I end up always with an even length because I'm always introducing 2 symbols if I apply a production rule that doesn't consist of just the empty string. So this is all you need for your context-free grammar to produce such a language. Now this language isn't terribly difficult to figure out, right? We've come up with other ways to describe this language in the past. So I thought we would do another example just to talk a bit more about patterns. So let's think about another one. So I want to try to design a context-free grammar for this language. Now, we haven't seen one like this yet, so I thought we would play around with this. So I'm going to call it L4O. I thought it was a neat name at the time, okay? So it's going to consist of binary strings. Binary strings, where it's going to be that there's exactly 4 zeros. There's going to be exactly 4 zeros in the string. And every 0 and every 0 has a 1 after it. So you might ask, Dan, why are you bringing up an example like this? Well, this is something that you might run into if you're talking about, say you have a particular format in place, like so frequency of how many times a symbol can appear. We've seen actually examples sort of like this in the past, but notice that this actually enforces that if a symbol appears, that there has to be another one that appears right after it. That's what makes this a little different. So let's think about how we might go about this. So I always like to think about almost like the string is like a template. I would like to see what the string has to look like. Now we know it has to have exactly 4 zeros, so it's always going to have a form that looks like this, where it's going to have 4 zeros. There might be stuff before it. There might be stuff in between here. 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 However, if you look at our definition of this language over here, it says that every 0 has a 1 after it. So you know right away that there has to be a 1 that comes right after each one of these zeros. The minute you observe this, it makes everything much easier. So, however, notice that I still have these blanks. These blanks, in all of these spots, it has to be what kind of symbol can go there. Can I put zeros in there at all, at these blanks? So all these blanks may include 0 or more 1s, right? So the minute you see this, you get a nice idea of what the string has to look like. So I usually recommend you, if you can, write it out, like, especially if it has a substring that you're interested in with a particular form. This is usually a nice way of going about it. We've done something like this in the past. So here's a suggestion. Let's first design what happens with all these blanks first. See what these blanks need to look like. So I'm going to start off by giving a production rule that represents that. So of course, there could be 0 1s right there. So I'm going to include a production rule for the empty string. However, it could be just like we used in the past. We may want to have include 1 or more 1s. So this allows me to introduce another 1 in, and then I can reapply the rule where I can either terminate this process of generating 1s, or I can apply another 1. So append another 1 to the string. So this will account for those blanks over there, right? Because it says that we need 0 or more 1s in there, right? And this, we've seen actually how to do this in the past. So a natural question now is, how do we get it so we get the rest of this? And the lovely thing is that context-free grammars have a lot of versatility for how we can go about that. And you're going to ask, oh, Dan, are we going to have a bunch of different production rules? You're going to be very surprised that once you've laid out the form like this, it actually makes things much easier, because now we have what, in effect, a way of saying, okay, there's something that looks like a terminal, but we have these blanks. Now we know how to represent those blanks, right? Those blanks are these guys right here, right? That's what those are. So the minute you notice that, all I'm just going to do is write out what this is, where every one of the blanks are, that's where A is going to go. Because I can always substitute in a 1 in there, or nothing, right? So first blank, then I have 0, 1. Then I have the next blank, 0, 1. Then I have the next blank, 0, 1. So how many do I have? 1, 2, 3. That means I'm going to need another 1, right? 0, 1. Because remember, the 1s have to come. There always has to be a 1 after the 0. And then, of course, I have a blank at the end. So notice this looks a little more beefy of a production rule, but most certainly this captures that form over there. So if you notice that, that's the form that we need here. So notice that here we just came up with a couple of different types of patterns. And the idea here was to come up with an arbitrary pattern, because we just didn't really care about what the symbols were. What I cared about was the length of the string. Here, we try to come up with a template of sorts. And once I have the bits and pieces, I work on the smaller bits and then I work my way up. That's at least how I think about it.